Hello, this is Eric Hernandez from the University of Vermont, Department of Civil Engineering, and today I want to share with you the concept of equilibrium, explained in 5 levels of difficulty. The goal of this video is that by the end of it, regardless of your level of scientific or engineering training, you would leave with an enhanced understanding of the concept of equilibrium and maybe even a little curious about some ideas that maybe you can go and research a little more on your own. So let's get started. Level 1. Level 1 is probably the most basic level of understanding of equilibrium. Basically, two forces, equal and opposite, acting at a point. So if you think of two people pulling on a rope with equal force, they will be in equilibrium. If one of them doesn't pull with the same force, then you would think they're not in equilibrium. Now, a step up from that would be level 2. Level 2 generalizes this idea to multiple forces acting at a point. So consider here, let's say, a 10-pound weight hanging from 2 inclined cables. These 3 forces will be in equilibrium if they form a closed circuit or polygon. In this case, a triangle, because there are 3 forces. But this generalizes to any number of forces acting at a point. The same holds true. If they are in equilibrium, they must form a closed circuit or a polygon. An everyday example of this can be found in what structural engineers call a truss or a truss bridge. The truss is composed of many members, usually arranged in triangular form. These members meet at points that we call joints, and the forces coming in and out of those joints. Here I'm drawing an example of a joint in a truss bridge. You can draw those forces all acting at a point, and the way to check if they are in equilibrium is by drawing them, as some people like to call, tip to tail. And if the forces form a closed circuit, they are indeed in equilibrium. The order in which you draw the forces doesn't matter. They will form different circuits, but they will all be closed circuits if they are in equilibrium. Now, a step up from this would be multiple forces acting at multiple non-collinear points. In this case, it's not enough to say that the sum of forces equals to 0. Because when you have multiple forces acting at multiple non-collinear points, you can end up with a situation of two forces equal and opposite, but acting eccentrically, like this. And then in this case, these forces are not in equilibrium because they also generate a rotational effect, which we call torque or moment. So in addition to the sum of forces being equal to 0, the sum of moments or torques also has to be equal to 0. Mathematically, this is the cross product between the distance and the force as vectors. Another way to see this is that the moment or torque of a force is the magnitude of the force times the distance perpendicular to the force to that point. So if you have a force here and you want to determine the moment of that force with respect to this point, you would find the distance from that point perpendicular to the force and multiply that force, the magnitude of that force, times that distance, and that gives you the torque, which we represent with a rotational arrow like that. Now let's look at an everyday example of this. Two people standing at different sides of a pivot point or fulcrum. How do we know if they are in equilibrium? How do we find an equilibrium position? Well, they have different weights, so they have to be placed at different distances such that their moment or torque with respect to the fulcrum is equal. In the case of the lighter person on the left side, is 500 newtons times 2 meters. That gives you 1,000. And on the right side, you have somebody twice as heavy, so they have to be at half the distance, which in this case would be 1 meter. And so they are in equilibrium. Notice that regardless of their position, the sum of forces will always be 0, but the sum of moments not necessarily, unless they are at specifically points that generate 0 total torque. Okay, so that covers level 1, level 2, level 3. Now level 4 is understanding equilibrium from the perspective of virtual work. So first of all, what is work? Well, the work of a force, if you draw a force, the work of a force is the force multiplied by the displacement collinear with the force. So if you have a point here, let's call that point A, and you have a force acting on A, and that point moves, let's call this R, that distance, the work of that force is the magnitude of the force multiplied times the amount of displacement aligned with the line of action of the force. So that's the work. Now, what is virtual work? Virtual work is the idea that if a set of forces is in equilibrium, acting on a body, and you imagine that that body experiences a differential displacement consistent with the constraints, then the sum of the differential work of all the forces will be equal to 0. Here, this is the basic equation of virtual work, and F is the force, and D delta is the differential virtual displacement. So if we go back to the seesaw problem, let's imagine a virtual differential displacement consistent with the constraints. In this case, the constraint is that the center point remains fixed, so our seesaw can only rotate about that point. And in that case, if we imagine a differential rotation here, d theta, that rotation generates a displacement, differential virtual displacement at the point where the forces are acting. In this case, this displacement here will be 1 times d theta. In this case, the displacement will be 2 times d theta. And if we do the sum of the virtual work, we find 500 times 2 d theta minus. Why minus? Because here the displacement is going opposite to the direction of the force. So we have 1,000 times 1 d theta. And that indeed is equal to 0. So that's the understanding of equilibrium as virtual work acting on a body, which may have some constraints, right? Now, finally, Level 5 is dynamics, forces in motion. What happens when forces are acting on different bodies that are moving with certain acceleration? Well, we know from Newton's equation of motion that F equals ma. Now we can rewrite this as F minus ma equal to 0, and think of ma as the inertial force. If you do that, you end up with an equation that basically goes back to the basic idea of sum of forces equal to 0, but now you have to add this inertial force, which represents the tendency of the body to move, to not move, right? To want to stay in its position. So if you think of, for example, a pendulum, an everyday example of a pendulum rotating around a pivot point or fulcrum, you draw the forces. In this case, you have gravity going down, which can be decomposed into the tangential component here in blue and the radial component here in red. And then in addition to that, you have the restraining force coming from the rod holding up the mass. That's a force T. So if you look at T and you look at mg, which is the gravity force, they are obviously not in equilibrium because they're not two forces equal and opposite. In order to restore equilibrium, you have to add the inertial force. So if you do that, you find that, let's say you write the equilibrium equation in the tangential direction. You have mg sine of theta, and then you write minus ma. Well, ma is going opposite to that, so you need to say plus m, and in this case a, the tangential acceleration, is equal to the rotational acceleration times the length of the pendulum, right? So then here you have m l theta double dot equal to 0. You divide by m and you divide by L, and you get the standard pendulum equation that you can find in any dynamics book. And this is a differential equation that governs the motion of a pendulum. So again, level 5, understanding of equilibrium, is dynamics. So quickly, let's review. Level 1, two forces equal and opposite. Level 2, multiple forces acting at a point. Level 3, multiple forces acting at multiple non-collinear points. Level 4, virtual work. And level 5, dynamics. Well, thank you for your attention, and I hope that you really enhanced your understanding of equilibrium. And as I always say, stay in equilibrium, my friends. Until next time.